Our lesson 6.5 is entitled Pascal's Principle and Hydraulic. If you are new to this channel, please do not forget to subscribe, hit the bell, and do some comments. I post educational videos at least twice a week. So let's get started. Our lesson 6.5 has the following goals. 1. To explain the Pascal's principle and hydraulics and its applications to daily life. Number 2. To solve problems involving Pascal's principle and hydraulics. Who is Pascal? Blaise Pascal, from 1623 to 1662, was a French mathematician, physicist, inventor, philosopher, writer, and Catholic theologian. He was a child prodigy who was educated by his father, a tax collector in Rouen. He made some significant observations about fluid and pressure. He noticed that the shape of a container had no effect on pressure. He also noticed that pressure applied to an enclosed fluid is transmitted undiminished to every part of the fluid, as well as to the walls of the container. When it says enclosed fluid, that means that in order for Pascal's law to be true, you have to be looking at a liquid in a closed container. The Pascal's principle is stated as any external pressure applied to a fluid is transmitted undiminished throughout the liquid and onto the walls of the containing vessel. This means the pressure is constant at all points. Applications of Pascal's principle. 1. The hydraulic lift. Hydraulic means denoting, relating to, or operated by a liquid moving in a confined space under pressure. Hydraulic lift is versatile in its utility. It has hydraulic apparatus which is used to lift heavy objects. In the case of hydraulic lifts, force applied creates lift and work. It is based on the principle of equal pressure transmission throughout the fluid. In the figure, a narrow cylinder A is connected to a wider cylinder B, fitted with airtight pistons filled with an incompressible fluid. When pressure from piston A is transmitted to piston B lifts the heavy object like big machines or vehicles. The hydraulic lift technology has widespread applications in the industrial, construction, transport sector, and so on. The hydraulic jack. The hydraulic jack consists of two cylinders, a larger and a smaller one, and these two cylinders are connected. When its handle is pressed down, a valve closes and the small piston forces the fluid, through another valve to a larger cylinder, which then produces a large force to be transmitted to the load. Therefore, we can say that when force is applied, the pressure is exerted throughout the volume and surface of the cylinder. The handle is moved up and down repeatedly until the load is sufficiently lifted up by the hydraulic fluid flowing buffer tank to the small cylinder. Hydraulic jacks are highly advantageous in the automotive industry and are often used to lift cars above the ground level for repair and maintenance. Hydraulic brakes. One of the most common examples of Pascal's law is the hydraulic braking system present in the automobiles. Every time you see a car come to a halt, the principle of Pascal's law comes into action. A number of components form the braking system in cars. When force is applied on the brake pedal, there is a movement of the piston and rod in the master cylinder. A liquid, which is known as brake or hydraulic fluid, enclosed in the container, is used to transmit the pressure from the brake pedal to the wheels of the vehicle against the brake disc or brake drums. The frictional force between these force components causes the vehicle to stop. The hydraulic press. Recall that the pressure P, force F, and area A are related to each other by the formula P equals F over A, where P is the pressure in Pascal, F is the force applied in newtons, and A is the area in meters squared. When a small force F1 is applied to a small area A1 of a movable piston, it creates a pressure P equals F1 over A1. This pressure is transmitted to and acts on a larger movable piston of area A2, which is then used to lift a car. Thus, we have P equals F1 over A1 equals F2 over A2 since pressure is constant all throughout. Let us do some examples now. Example number 1. The small piston of a hydraulic lift has an area of 0.20 meter squared. A car weighing 12,000 newtons sits on a rack mounted on the large piston. The large piston has an area of 0.90 meters squared. How large a force must be applied to the small piston to support the car? Solution. We use the formula P equals F1 over A1 equals F2 over A2. Here, we are given the following values. Area 1 of the small piston is 0.20 meters squared. F2, which represents the load or the weight of the car, is 12,000 newtons. A2 equals the area of the larger piston, which is 0.90 meters squared, and we are required to find the force that must be applied to the small piston to support the car F1. Solving for F1, we get F1 equals A1 times F sub 2 over A2. Substituting the given values and simplifying, F1 equals 2,666.67 newtons. Example number 2. A 20 newton force is exerted on the small piston of a hydraulic system. The cross-sectional area of the small piston is 0.05 meters squared. What is the magnitude of the weight that can be lifted by the large piston, which has a surface area of 0.10 meter squared? Again, we use the formula P equals F sub 1 over A1 equals F sub 2 over A2. Here we are given the values. A sub 1 is 0.05 meters squared. F sub 1 is 20 newtons. A sub 2 is 0.10 meters squared. F sub 2 is the weight that can be lifted by the large piston, which is to be found. Solving for F2, we get F2 equals A2 F1 over A1, substituting the given values and simplifying, F2 equals 40 newtons. Example number 3. In a machine shop, a hydraulic lift is used to raise heavy equipment for repairs. The system has a small piston and a large piston with a cross-sectional area of 0.21 meters squared. An engine weighing 2,700 newtons rests on the large piston. If a force of 900 newtons must be applied to the small piston in order to lift the engine, what is the cross-sectional area of the small piston? We use the formula P equals F1 over A1 equals F2 over A2. Here we are given the following values. A sub 2, which is the cross-sectional area of the large piston, is 0.21 meters squared. F sub 2 is the load, which is 2,700 newtons. F sub 1 is the applied force, which is 900 newtons. And we are required to find the cross-sectional area of the small piston A1. Solving for A1, we get A1 equals A2 times F1 over F2. Substituting the given values and simplifying, A1 equals 0.07 meter squared. Example number 4. A barber raises his customer's chair by applying a force of 150 newtons to a hydraulic piston of area 0.01 meter squared. If the chair is attached to a piston of area 0.1 meter squared, how massive a customer can the chair raise? Assume the chair itself has a mass of 5 kilograms. We use the formula P equals F1 over A1 equals F2 over A2. And we are given the following values. F1 is 150 newtons, A1 is 0.01 meters squared, A2 is 0.1 meters squared, and we are required to find F2. Solving for F2, we get F2 equals A2 times F1 over A1. Substituting the given values and simplifying, F2 is 1,500 newtons. If the maximum force on the chair is 1,500 newtons, we can now determine the maximum mass, which can be lifted by recognizing that the force that must be overcome to lift the customer is the force of gravity. Therefore, the applied force on the customer must equal the force of gravity on the customer or his weight. From F equals mg, solving for m and substituting values, we get m is F over g equals 1,500 divided by 9.8 equals 153 kilograms. If the chair has a mass of 5 kilograms, the maximum mass of a customer in the chair must be 150 kilograms minus 5 kilograms or 148 kilograms. Thanks for watching. Please do not forget to subscribe.